Hi everyone, this is my second lab report. And quick introduction is the purpose of the lab is to observe an object falling from rest, then analyze its motion in tracker to find its position and velocity data, then utilize that data from tracker to build two models in Glowscript to predict the position and velocity data, and then finally compare the observed versus the predicted data on a graph. So we use some fundamental physics principles in this lab, specifically Newton's second law, which is Fnet equal to the change in momentum over the change in time, which then allows us to use the velocity update formula, where we can predict the final velocity of this system if we have its initial velocity, the net force, its mass, and a change in time, which then also allows us to use the position update formula, where we can predict the final position if we have its initial position, the average velocity, and the change in time. And the average velocity for a constant net force is the arithmetic average, and it is the final velocity for a non-constant force. We also look at the gravitational force near the surface of the Earth, which is the force felt by the system due to the mass of another object. And in the case of Earth, we multiply a negative times the object's mass and g, which is the acceleration due to gravity on Earth. And then we also looked at the drag force, which is the force that acts on an object in the opposite direction to its relative motion as it passes through air, where b is a proportionality constant. We also look at just net force in general, which is the vector sum of all the forces acting on the system, and we have two different net forces in this situation because we have two different models. A quick description of the models is that they utilize Newton's second law by updating the velocity and position to compute the predicted position and velocity. And the first model uses a net force equal to Fg, and the second model uses a net force equal to Fg plus Fd. Quick overview of results is that the observed data follows the same trajectory as the first model, but has a slightly different y position for each time step, and it doesn't follow the same trajectory at all really as the second model. So going into the methodology, I first observed a tennis ball falling from rest in the negative y direction, where the system is the tennis ball and everything else is the surroundings. And then I inputted that video into the tracker, analyzed its motion, and then was able to get position and velocity data from that, and the initial conditions as well, including the mass, its initial velocity and position, and the times, as well as its y component of position at a specific time. So going into the modeling, we use those initial conditions for each model and input them into the Glowscript code, as you can see on the right. And then for the first model, the calculation loop utilizes Newton's second law to update velocity and position with a net force equal to Fg. So we see that the proportionality constant is 0, the net force is just Fg, and then we utilize the net force to update velocity and position. The second model does the same thing, except that Fnet is equal to Fg plus Fd, where we do have a proportionality constant for the tennis ball. Then we calculate the gravitational force, then the drag force, and add those together for the net force, and then use that to update velocity and position. And then, as you can see, here's some of the Model 1 output with the raw data, as well as the graphs and the 3D representation, and the same for Model 2, and you can see some differences there that we'll talk about in 1 second. So some of the results and discussion is we first compare the observed data with the predicted data from each model. And you can see that the first model actually is a pretty good predictor of the trajectory of the object's motion, but still slightly different, whereas the second model with Fd plus Fg is not really close at all. And so some of those possible sources of error could be that the point mass measurements could have been more precise, and I might not have dropped the object completely straight down. And some of the conclusion is just that the what does it mean question, we actually have the computational model 2 with Fnet equals Fg plus Fd does predict a terminal velocity, because once the velocity of the system reaches about -1, it remains constant, meaning that the force of gravity in the negative y direction and the force of drag in the positive y direction are equal in magnitude, meaning that net force is equal to 0. And for our what if question, we do see that terminal velocity is the same for an object, even if it was thrown or dropped from rest. It would just take more or less time to reach that terminal velocity, and it also depends on the initial velocity of the system. And so if the initial velocity is less than the terminal velocity, it will accelerate until it reaches that terminal velocity. Whereas if it's actually greater than the terminal velocity, it will decelerate until it reaches the terminal velocity. Thank you.